one of which I guess you spent some time last term talking about, which is called the parametric method. Parametric surfaces are basically for each of x, y, and z, you have some function of two variables, Bezier curves and so forth. Kuhn's patches are all in this category. And these are the favorite of geometric designers because they're very fluid and stretchy, and you can mold and form shapes out of them nicely. The other way is algebraic. And that's basically surface defined by some function of x, y, and z, all points where that function value equals 0 are points that are on the surface. Algebraic surfaces are somewhat simpler to define for some of these special cases than parametric surfaces. And they're not maybe quite as plastic as the parametric surfaces, but they are sometimes a lot easier to deal with. Now, in each of these cases, the parametric and the algebraic, the mathematical form itself happens to make certain geometric operations convenient and certain other geometric operations inconvenient. And they're kind of inverses in this sense. For parametric curves, it's fairly easy to make line drawings of these things. Effectively, you just start plugging in little values for u and v and step u along by small amounts and plug it in, and you get this list of x and y and z's, and so you trace a line along that. Plug in incremental values for v, and you get x's and y's along the v parametric lines, and so you can get this, you can make a mesh wireframe drawing of these things fairly easy. For shaded images, however, that is raster type displays, the parametric surfaces are somewhat harder to deal with because basically what you have is somebody hands you an x and y value, which is a pixel value on the screen, and you have to solve these two equations to find a u and a v value and plug that into the z thing to find what the z is at that u and v. And these two functions might be something pretty bizarre and not easy to solve for. On the algebraic sense, the inverse is the case. Just the reverse of the above. Line drawings are a little bit harder to do because you have to, again, find the place where the algebraic surface has some edge. It requires solving some equations, which may or may not be simple to do. But making shaded images of it, raster images, is somewhat easier because you just plug an x and y value in here and solve for the z. Algebraic surfaces are good for sorts of situations where you're asking a question, here's a point, is it on the surface or not? Parametric curves are surfaces are good for answering the sort of geometric question of, give me a whole bunch of points that are on this surface. Now, the algebraic curves, you can use any function you like for this f of x, y, and z. One that you've probably already played around with is just a linear function. I'll start tossing w's in here, so we'll be using homogeneous coordinates. Linear function of x, y, z, and w. Anything that satisfies that lies on a plane someplace. And there are various geometric things that that I presume you've learned how to do with planes. Now, you can model real objects with this, but it's generally a bit of a nuisance. It's quite often easier to model the planes as just the list of vertices surrounding the edges of the plane. The next stage of complexity here is going up from linear or first-order equations up to second-order equations. And second order equations and surfaces defined by them are called quadrics. And the general all-around equation for a second order surface is something like this. Lots of terms. We have all possible combinations of terms where the sum of the exponents of the x and the y is 2 here. We have an x squared, and an xy, and a y squared, and a yz, and a yw, and a z squared, and a zw, all possible permutations of that. And we look in here and we discover we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 coefficients. Kind of 10 values here which determine which of the many second order surfaces we've got. Now, there's sort of two parallel developments that I want to go on here. We can talk about second order surfaces in 3D where you have x, y, z, and w defining a surface, and there's second order curves in 2D where you have the z terms just don't appear here, and the mathematics is virtually identical for them, except you're just dropping down one dimension. So I'll kind of mention both of the equations simultaneously as I go along here. What sort of surfaces are you likely to come up with? You know, what the solutions to these things? They're generally going to be what you expect, like conic sections. 2D homogeneous and 3D homogeneous case here. Second order curves are going to be conic sections like circle, ellipse, parabola, and hyperbola, and a few others. The 3D homogeneous case are going to be kind of the 3D analogs of these things. There's ellipsoids. I can take a sphere as being a special case of an ellipsoid. It's one where the axes are all the same. Paraboloids, hyperboloids, and there's two flavors of hyperboloids. They're basically one where the hyperbola is swept around like that, making what looks like a nuclear reactor cooling tower. And there's the one where the thing is swept around the other way, making kind of two bumps facing each other. Now, in addition to these things, there are certain degenerate cases that show up. Certain combinations of numbers go in. You can imagine in the conic section case, say a hyperbola, which looks something like that. As you crank up certain of the parameters, you can make the point on the hyperbola get sharper and sharper and sharper until when some degeneracies happen, the points actually touch. And so for some sets of parameters, you actually get just two straight line segments that intersect. In addition, thing gets doubly degenerate, you can get two coincident lines, and there's a situation where you can get a situation where there's only one single point that satisfies the equation. It's a whole list of things like that. And similarly down here, there are some degenerate 3D curves. Cylinders, for example, with various cross-sections. Elliptical cross-sections or hyperbolic cross-sections or parabolic cross-sections, so there's kind of three different types of cylinders. Intersecting planes, just as two hyperbolas can get degenerated into two intersecting lines. Two hyperboloids can degenerate into two intersecting planes. And there are a few other similar things like that, two coincident planes or a single point, whatever. So what we'd like to do is to establish a little bit of order in all of this mess. So first of all, let's try our key ordering technique, which is to write everything, if possible, as a matrix. First of all, let's try to write this equation here as a matrix, some sort of matrix product. And I will just pull a rabbit out of a hat, and I will say running out of space here. Probably ought to wait till I write this down before you start copying it, otherwise you will have the same problem that I'm having. E F over 2, G over 2, Now, I maintain that this vector times this 4 by 4 matrix times this vector equals 0 is really the same equation as what I just wrote down here. In fact, what I've done is kind of split each of these terms, like the bxy term, into two pieces, putting it up here and down here. As it happens, these two slots in the matrix can take on several combinations of values as long as their sum is equal to b. And so you could have b up here and 0 down here if you like. But what I'm doing is trying to make it so this matrix is symmetrical, because symmetric matrices have some other useful properties. So what we've got here is a symmetric 4 by 4 matrix. All the divide by 2's sort of clutter things up a little bit, so we can rename things with capital letters and just use the same value on each side. So a symmetric 4 by 4 matrix, we'll call Q for quadric, then represents one of these second-order surfaces. And with the assumption that the way you actually see what the surface is to multiply x, y, z, w on this side and as a column on the other side, and any points which satisfy this equation lie on the surface. Now, similarly in the 2D case, what you'll wind up with is a 3 by 3 symmetric matrix with the same, just a shorthand representation for the same sort of second-order equation, xyw times 3 by 3 matrix times xyw equals 0. And that will give you surface second-order curves. Now, let's take a couple of simple examples here. If we take Q as being the matrix which looks almost like an identity matrix, except it's got -1 down here instead of +1. If you plug in x, y, z, w times these things and multiply it out, you discover that this stands for the equation x squared plus y squared plus z squared equals w squared, which is a unit sphere centered at the origin. And looks something like this. Now, any point which is inside the sphere, when we multiply it, like, for example, the origin, 0, 0, 0, 1, we multiply by this thing and we get a negative number. Any point which is outside the sphere, we multiply it by this thing and we get a positive number. So, general point to keep in mind is that on the sphere it's 0, inside the sphere it's minus, and outside the sphere it's plus. Now, in general, quadric surfaces have the same general nice homogeneous property in that any non-zero scalar multiple of that matrix is going to still represent the same shape, right? Because it's blah, blah, blah equals 0, and so you can multiply 0 by anything, it stays the same. If you multiply this by a negative number, however, the sense is reversed of whether something is inside or the outside. So what we're going to do is keep it in this state right now. At least you multiply it by positive scale factors if you want to. Things get a little bit overly difficult if you multiply it by negative scale factors. Now, the next thing we want to be able to do with these things before we draw them is to go through a little bit of simple geometric operations of what you might want to do with spheres and whatnot. For example, transformations. Suppose somebody hands you this unit sphere sitting at the origin and says, I want to translate this by this 4x4 homogeneous transformation matrix, which has a translation and a rotation and a scale and whatnot. What's the resultant 4x4 matrix which stands for the transformed shape? Well, we can do that kind of in the same way that you can introduce transformations of planes, in that we start out with this equation here. This is in the original coordinate system. And what we want to do is to find the new matrix, which we'll call Q hat, say, which satisfies the equation x, y, z, w hat. This is a transformed point times a transformed thing equals 0, right? Now, somebody's handed us the matrix which transforms this point into this point. So we've got that, and we'll call that T. This is sort of the definition of what x, y, z, w tilde is. It's what each point multiplied by this transformation matrix gives us. And what we'd like to do is to find out what Q is in terms of Q tilde is in terms of T and the original Q. Basically, it involves just plugging one of these equations into the other one. And if you take this and plug it in here, you get that. And it's just substituting the expression for the transform point in here. And if you compare this equation with that equation, with a little bit of engineering hand-waving, we can say, since the first and the last halves are pretty much the same, we can extract out the middle slice and say that those are the same as well. That's not strictly true in linear algebra. Various scale factors can crop in and so forth, but it satisfies us for the time being. Now, this is sort of the inverse of the relationship we want. We want to get Q tilde in terms of Q, not the other way around. So we just start multiplying, move the T to the other side by some multiply by the inverse. And then move this T to the other side by post-multiplying by the inverse. And here's the punchline. Somebody hands you a matrix Q, which represents some second-order surface, and they hand you a transformation matrix, T, which transforms points. In order to find the transformed quadric surface, Q tilde, you pre-multiply by the inverse of the transformation, and then post-multiply by the transpose of the inverse of the transformation, and this gives you the final Q.
Shouldn't that really be the inverse of the transpose?
I believe they're commutative in this case.
Yes, it should be. Okay, second point, what happens if your matrix T is singular?
If your matrix T is singular, you're in trouble. It means that, well, let's see, there's an answer to that, but let me defer that for a second. One comment that I want to make about this is there's a name that mathematicians have come up with for things that do this. They're called tensors. That transform in this way. If somebody hands you some geometric construct which in one coordinate system has a certain set of values, and in order to transform it into another coordinate system, you wind up pre-multiplying by a matrix and post-multiplying by the other matrix, then that thing is called a tensor. Q is a tensor. Now, there are several flavors of tensor as well, and because of the fact that you multiply by T inverse here, it's called a contravariant tensor. If you were to multiply by T, it'd be called a covariant tensor. This is all just to enhance your store of buzzwords. I don't expect to use this explicitly, although it's good to be able to tie it into what mathematicians mutter about every now and then.
I believe controversy is one word. You really want to be
Well, I didn't have enough room on the one line to. Can't get away with anything in this class. Okay. Now, what happens if T is singular? If T is singular, that means that basically you are losing information when you transform things. If you take, say, a cube, transform it by a regular transformation, it turns into maybe some distorted cube and so forth. But if you transform it by a singular transformation, that means it's going to get squashed flat in at least one dimension, right? And if you transform a sphere by a singular transformation, that means it's going to get squashed flat or stretched out infinitely far in another direction. And so what you wind up doing is the following thing. In fact, using T inverse here is a little more specific than is necessary. Now, I'm not sure what the official notation is on this thing. I've seen it called T star. T star is almost the inverse. Sometimes it's called by many people the adjoint, although I think that actually refers to, that particular term is somewhat nebulously defined. It's also sometimes called the generalized inverse. What is this? How do you come up with this? Remember the first time I came in here and started talking about, here's a handy trick for inverting matrices. You start taking the determinants of the submatrices and you start switching the signs in this checkerboard fashion, and then you transpose it. The last step was dividing by the determinant of the original matrix. That's the only step that's going to get you in trouble if this thing is singular, because the determinant is 0, right? If you just leave out the last step, go through the first 3, and stop there, what you've got is this, T star, the adjoint. This is equal to the determinant, or equal to the inverse of the matrix, except for some arbitrary non-zero scale factor. Now, since in all these cases any non-zero scale factor times the matrix is the same shape, we don't really care if there's some arbitrary non-zero scale factor in here, so we can get away with just multiplying by the adjoint. Now, if T is singular, the adjoint still exists, and it has possibly perfectly reasonable numbers in it. It'll probably have a lot of zeros in it, but not all zeros. There'll still be some good stuff in there. And so when you multiply T star times Q times T star transpose, you'll get another surface, which is what would happen when you transform the original surface by the singular transformation. And it will be one of these singular shapes, too. The sphere is going to turn into something like a cylinder or a set of intersecting planes or something like that.
So is the bottom line that whenever you're going to use an inverse?
Speak into the microphone.
Whenever you're going to use an inverse, when you have a homogeneous coordinate formulation
Right.
of the equation, you don't have to go through the division by the determinant?
That's right. You have to kind of keep in the back of your mind that you're not doing that, because there are certain cases where that'll come around and bite you, but in most cases you can get away with not bothering dividing by the determinant. Generally, you have to watch out when you start dealing with things that deal with explicit distances, for example. Explicit distances don't fall into the formulation of projective geometry, which is what all this homogeneous coordinate thing is about. They introduce an asymmetry into the equation. And so as soon as you start doing that, then you have to worry a little bit about keeping all your scale factors straight. Now, how can we, next little tidbit here is how to categorize the different types surfaces. I'm going to sort of rush through this just to kind of show you what it is, but it's not directly amazing for what we're going to use to make pictures of it. If Q is singular, that is, if the determinant of Q, just taken as a matrix, is equal to 0, then that means you've got one of these degenerate cases. You've got one of these, it's a cylinder or a set of intersecting planes. It's not just a ellipse or a sphere or something like that. And in general, you can divide these things into categories based on the eigenvalues of Q. What are eigenvalues? Suppose you have a matrix. How do you picture this matrix? Well, I find it useful to picture a matrix as, let's take a whole bunch of points in a cloud, say on a sphere, and we'll pass all the points through this matrix as though it was a transformation. So each point's going to transform to a different place. You can sort of visualize the matrix as what shape this sphere turns into after all the points have changed into, have been transformed by it. As long as the matrix is non-singular, the thing is going to be some elongated ellipsoid or something like that. If the matrix is singular, it's going to get squashed flat in at least one direction, so it's going to turn into a disk. And if the matrix is doubly singular, it's going to get squashed flat along 2 dimensions, so it'll turn into a line segment, things like that. The eigenvalues of a matrix are the semi-minor axes of this ellipsoid that the sphere turns into. You start out with a sphere like that. Multiply all the points on the sphere times this matrix, and you're going to get, in general, some sort of ellipsoid. And if you measure the semi-minor axes of that ellipsoid, I presume everybody knows what semi-minor axes are, you'll get 3 different numbers, and those are the 3 eigenvalues of this matrix. In the case of a 3 by 3 matrix. In the case of a 4 by 4 matrix, you have to start imagining hyperspheres, but it's the same general idea. Going along with eigenvalues, there are eigenvectors, too. The eigenvectors are just the vectors that go along the semi-minor axes of the sphere. Now, if the matrix is singular, that means one of these things is going to be squashed into a disk, right? So one of these semi-minor axes is going to be 0. And if the matrix happens to be doubly singular, 2 of them are going to be 0. And so in a certain sense, the eigenvalues of a matrix tell you a little bit more interesting information about the matrix than just the determinant of it. The determinant of it tells you it's singular or not, but the eigenvalues kind of tell you how singular and kind of in what way. And in addition, the determinant of the matrix always happens to be equal to the product of the eigenvalues. Now, this is just kind of telling you the punchlines of some linear algebra rather than deriving it, but it's kind of the practical information you need to know for the time being. So let's take a look at the possible combinations of values these eigenvalues can take on. What we're really interested in here is if an eigenvalue is positive or negative or 0. The exact magnitude is not real important in categorizing the shapes. 4 by 4 matrix, homogeneous tensor representing a second-order quadric surface. Suppose all 4 eigenvalues are positive or all 4 eigenvalues are negative. What does that represent? Nothing. There aren't any points which will satisfy this. How can we come to this conclusion? Let's take a look at a simple matrix which has all 4 eigenvalues positive. The simplest way to construct a matrix with some desired set of eigenvalues is just to make an identity matrix with just the eigenvalues along the diagonal. These have 4 positive eigenvalues. If we were to think of this thing as one of these Q quadric matrices, we take x, y, z, w, multiplied on both sides. We get x squared plus y squared plus z squared plus w squared is equal to 0, which means all 4 coordinates have to be equal to 0. That's the only way you can make them the sum of the squares equal to 0, which means that there really aren't any points that satisfy this. X, Y, Z, W, all 4 equals 0 is nothing, right? Whoop. Next case is 3 plus and 1 negative, or 3 negative and 1 positive. And for example, the sphere that we started out with a little bit ago had 3 positive and 1 negative eigenvalue. We're going to say conic section here, but that's a two-dimensional curve, but I'll say conic surface. This is spheres, ellipsoids, hyperboloids, paraboloids, and so forth are like this. 2 positive and 2 negative. I haven't looked this up. I think this is I'll give it a more common name, saddle point, also known as a hyperbolic paraboloid. Something of roughly that shape. I believe that's right. So these are all the combinations of all non-zeros. We start getting into singular things. I don't know if it's worthwhile going through all the combinations of this, but what you can do is, good exercise in just manipulating these things, is to go home and take all combinations of positive, negatives, and zeros that you can come up with, construct a matrix which has just got those numbers on a diagonal, multiply it out with x, y, z, and w, and see what surface you come up with. Things with zeros in here, 1 0 will give you things like cylinders and other sorts of degenerate things like that. 2 zeros will give you something that's doubly degenerate, which will be intersecting planes, and 3 zeros will give you intersecting lines, I believe.
Can you say just briefly how you compute the eigenvalue?
Somebody hands you a arbitrary matrix on a plate and says, what are the eigenvalues? You do the following game here. Yeah, right. We must not rely on the computer to do everything for us. It still requires a little bit of human intelligence here. Another way of defining eigenvalues is, and eigenvectors are, if you multiply a vector times this matrix, an eigenvector times a matrix, you get the same vector except maybe scaled by some amount. The vector points in the same direction, but it might not be the same length is all. The new length, or the scale on the length, is the eigenvalue, and the vector itself is the eigenvector. Now, if you take this equation and solve it for p, you come up with something like this. I means the identity matrix. Basically, what you're going to do here is go through and say q11 minus lambda and so forth, q22 minus lambda and so forth. You're subtracting lambda off of the diagonal elements of q. Now, the only way that you can make this times this matrix be equal to 0 for an interesting vector is if this net matrix here is singular. That means the determinant of this thing is 0. You can symbolically take the determinant of this mess, which will give you a polynomial in lambda, solve the polynomial. For a 3 by 3 matrix, you're going to get a cubic polynomial, so you'll have 3 solutions. For a 4 by 4 matrix, you're going to get a 4th order polynomial, and we have 4 solutions. Now, another interesting punchline from the world of linear algebra is, as long as the matrix is symmetric, which we happen to like a lot because they're quadric surfaces, as long as the matrix you start out with is symmetric, all of the solutions, all of the lambdas here are going to be real. The eigenvalues of a symmetric matrix are all real, which is convenient for all this categorization thing. It's possible, since we're arbitrary cubic equation, we can come up with complex roots, but that won't happen as long as the matrix you start out with is symmetric. Okay. I have to avoid getting too deeply enmeshed in the mathematics of this thing because I happen to find it particularly interesting, although certain parts of it are more abstract than we need for the nuts and bolts of making pictures. Here's another little punchline which I'll throw out, which I won't try to prove. Here's a quadric surface, Q, P point times Q times point transpose equals 0. This tells you if a point is on the surface or not. Suppose you take a look at Q inverse or Q adjoint or Q star, whatever you want to call it. You don't have to divide by the determinant here. This turns out to be interesting in that if you take, well, in the case of surfaces, if you take the A, B, C, D coefficients of a plane in space, multiply it by Q star times the coefficients of the plane. If that is 0, then that means the plane is tangent to the surface. Here's a sphere, for example. And here's a plane. And if this product is equal to 0, then the plane is tangent to the surface. If it intersects the sphere, you're going to get a negative number. And if it's outside the sphere, you're going to get a positive number. I might have those signs wrong, but one way or the other. This turns out to be useful in solving some interesting geometric problems as well. Now, all of this stuff also, again, takes place for second-order curves as well. If you take a circle and you take the 3 by 3 matrix which represents the circle, and you take the inverse of that, you can tell if a desired line segment is tangent to the circle or not. Multiply the coefficients A, B, C of the line in front and behind the thing, and if it's 0, then the line segment is tangent to the circle. Yeah?
What's the transpose of a point?
Generally, we write points as row vectors, so it's x, y, z, w. The transpose of that thing is the column vector, like that. Now, since planes start out as column vectors, then the real plane, A, B, C, D here, is the plane, and the transpose of the plane is in front. As it happens, the notation we're using is sort of a graphic image effect here of taking a vector or a matrix and writing it out as a row or a column. That's pictorial in a sense. Generally, when you get into pure mathematics, they just write them as symbols with subscripts and superscripts for the indices. And so this is a shorthand notation of something. And when you start getting into higher order dimensions, this breaks down because you have to start talking about cubes of numbers and hyperdimensional arrays of numbers, which gets confusing. But as long as we stick to this, we can get away with it. Okay. Zing. When we're making pictures of a surface, we need to be able to find out where that surface shows up on the screen. And as I talked about last time, all the lighting models and so forth are very interested in finding out what the surface normal vector is, right? What direction, at least locally, the tangent to the surface is. How do we find the normal vector to an algebraically defined surface? Now, we can define this just in terms of an arbitrary function, not just second-order functions, but any bizarre function you might happen to come up with. The normal vector is constructed like that. You take the partial derivative of f with respect to x, that's the x component. Partial derivative with respect to y, that's the y component. Partial derivative of f with respect to z, and that's the z component. Now, this, of course, has to be evaluated then at the x, y, z point on the surface that you're interested in. What does this look like in terms of quadric surfaces? The function here is that, explicitly, right? Let's take just the x component of the normal vector. That is, let's take the partial derivative of this thing with respect to x. We can employ what winds up being sort of like the chain rule applied to vectors here, because we got kind of the product of two things with x here. So the derivative of this thing with respect to x is partial of this term times this plus the partial of this term times that. Right? That's the way that you take the derivative of the product of two things by the chain rule. It's the derivative of this thing with respect to x. 1, 0, 0, 0. Derivative of x is 1. Everything else is independent of x. So we have that times q. First term. And the second term is the other way around here. Partial of f with respect to x. That's the x component of the normal vector. Now, since q is symmetric here, these two terms are really the same. They're just kind of flipped relative to each other. So we can write the whole thing as that, right? Similarly, the y component is equal to blah, 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 except we got 0, 2, 0, 0 here. And the z component is equal to this, except that the 2 is down here and the 0 is up here. So that is the expression for the vector normal to the surface at any desired point. Just plug in the point x, y, z, w. And if it's on the surface, you'll get the normal vector. If it's not on the surface, you'll get something that's more or less reasonable. It'll be a vector kind of pointing away from the surface, but generally we're not interested in those so much if we're shading points that are on the surface. This is 4 by 3. There's only 3 components in the normal vector, right? Now, there's another way of saying this. Throwing out a lot of punchlines here without deriving them, just so that you can stash them away. It's interesting to go through and kind of convince yourself that these things are true just to get facility with what's going on. If we take an arbitrary point on the surface, multiply it by the Q, the matrix for the surface, we're going to come up with 4 numbers, right? These 4 numbers can be interpreted as the coefficients of a plane which is tangent to the surface at that point. Here's a sphere. Here's the point P. Sphere is represented by the matrix Q. Multiply P times Q, you'll get 4 numbers. Those 4 numbers will be the coefficient of this plane, which is tangent to the sphere at the point P. Another handy geometric thing to be able to do. And in fact, the first 3 coefficients of a plane equation, A, B, C, D, in general, you should remember this from last term, A, B, and C are the vector perpendicular to the plane, right? And D is in some way related to the distance of the plane from the origin. More amazing facts. We're now getting into the viewing geometry of this thing. We're going to draw these things yet. Be patient. We've got a sphere or an ellipsoid or something sitting out there, and we're looking at it. Now, when you see this thing, the most important part of it that you see is what's called a silhouette outline, right? It's the ellipse or whatever it is that projects on the screen. That's the curve that bounds the thing, right? Now let's assume that we have taken our sphere and we have transformed it someplace in space, and we passed it through a perspective transformation, so it's going to get a little bit bent and warped around, but it's still a second-order surface. This is a very nifty property of these things. because, you know, you take the 4x4 matrix for the perspective, the inverse of that in front, and transpose the inverse of that in back, multiply that. That's still going to be a 4x4 symmetric matrix, but it's the perspective version of it. So these shapes are closed under the perspective transformation. The eye is now out here at infinity, and so what we'd like to do is kind of find the outline of this thing that is going to be the silhouette outline of this thing as seen from the eye. Silhouette outline is defined by a place where the z component of the normal vector is equal to 0, right? Pointing perpendicular to the line of sight. The z component of the normal vector what we just got done figuring out how to calculate a second ago. You'll just extract off this one column of this matrix with all the 2's and 0's in it. That gives us the z component of the normal vector, right? Now suppose we draw a little box around these two things. Q times this column of 0, 0, 2, 0. If we were to multiply those together, we're going to get a set of 4 numbers in a column. X, Y, Z, W times these 4 numbers equals 0. These 4 numbers, again, can be thought of as a plane. This is the perhaps astounding fact that the silhouette curve in space lies in a plane. Now, if the sphere happens to be exactly along the line of sight, the silhouette plane is going to be perpendicular to the line of sight. We're not too amazed that, you know, the silhouette plane is a flat plane. But if it's off the line of sight and we have a weird field of view, this thing is going to be distorted as an ellipse or something like that. The silhouette plane is going to be tipped towards us somehow. But it's still a plane, and the silhouette outline is still a conic section curve in space. Now we can generalize this a little bit further in that, again, this is a punchline. It can be proven, but when the eye is in infinity, that means the homogeneous coordinate of the eye is 0, 0, 1, 0. It's in the z direction, but it's on the plane of infinity, so the w component is 0, right? This vector here and that vector there have an awful lot in common, don't they? And in fact, what you can do is take any point in space you like, multiply it by this vector q, and you'll get a plane. And this plane is called the polar plane. I don't know what polar has to do with it, but it's a plane, and it has the following interesting property. Here's the sphere. Here's the arbitrary point out here. And if you multiply this times this, you'll get a plane in space. That plane will be the silhouette plane of this object as viewed from this point P. If you position yourself here and look at the object, then where the object intersects the plane, that's the curve that you would see in the outline. Another way of stating that is saying, suppose we take the tangent cone from P to this sphere. Where that cone, tangent cone, intersects the surface, that curve is also going to be the silhouette plane. What class of objects have silhouette planes? Anything that it makes sense to have silhouette planes. Multiply P times this thing here. If it's a cone, you get kind of both lumps of the cone, of course. That has a silhouette plane, but it's actually going to be 2 intersecting lines, right? So cone is a degenerate quadric surface, and so it has a degenerate silhouette plane. If you start with a point that's inside the object, however, you're not going to get a silhouette plane. So it depends more on the position of the object rather than the shape of the object. You're going to get a plane, but it's going to be a plane that's off in the boondocks someplace and doesn't intersect the surface at all. Okay. Now, suppose we want to build up an object out of these things. the typical modeling technique for using quadric surfaces is to define a few simple primitives like unit sphere at the origin and model them more in terms of transforming them to where you want to be rather than trying to immediately blast your way into the surface initially. And so you start out with a canonical matrix for the standard unit sphere at the origin, and you model that as the set of transformations, rotations, and scales that position it in space where you really want it to go. And so in a sense, the model is as much the transformation applied to the standard sphere as it is the sphere itself. And so a modeling system using this thing will have generally a unit sphere, and it will have maybe a unit cylinder and a few things like that, which are then shaped and scaled and skewed or whatever necessary in order to put them in the right space. But ultimately, you're going to wind up with the matrix Q that you want to draw a picture of. The matrix Q is going to be formed of several pieces, and it's useful to give these pieces names because we'll come back to them in a bit. First, we'll just define what the transformation is. I always write these expressions to define things. If you take a point, multiply it by the matrix T, times the perspective transformation, gives you a pointed screen space. What I've done is taken the net transformation and split it into two pieces. T is the transformation which is the composite of all the modeling transformations for shrinking it to be the right size and putting it where you want on the net composite object, and maybe scaling it different amounts to get a cigar-shaped thing. And the viewing transformation, which is orienting it with respect to how you want to look at it so that you're looking down the z-axis and it's sitting out there in front of you somehow. The important thing about T, however, here is that when you multiply some objects' points by T, they're still in some real coordinate space, in that we haven't done perspective distortions on them, or we haven't done non-square pixel distortions or anything like this. So you can still calculate normal vectors in this space. That's where we're going to do all the lighting, right? We can't mash up the orthographicness of the coordinate system when we're computing normal vectors and distances for lighting. The perspective transformation P here represents everything after that you have to do. That's the perspective transformation with the field of view and so forth that squashes things that are far away in closer to you, and the transformation that puts it on the screen perhaps with non-square pixels so the thing has to be stretched out a little bit more in X than it is in Y and so forth. And this is what defines the geometry of how it's going to map onto the pixels. And we're going to have to deal with these things separately because the lighting calculations are done at this point, and then geometric calculations are done at this point. So the final matrix Q, then, is going to be equal to this, where S, for example, is just a unit sphere matrix with, all the zeros and 1 minus 1 in it. And we'll come back to that somewhat later on. Now let me show you an example of what an object might look like that has been modeled with all these things. Does this thing zoom in and out at all? Can back off a little bit. Issue of Byte magazine last November showed an image made at the New York Institute of Technology. And this is out of a movie that they're attempting to generate called The Works, which is a movie about robots. And one of their primary image modeling and rendering systems has to do with quadric surfaces, second-order surfaces. This giant ant and the little critter robot down here and the tuck and roll upholstery and the cap nuts and everything are all done with quadric surfaces or pieces thereof. And you can see, like along in here, these are little chunks of cylinder going down the lumps of the leg. The body of this thing is an ellipsoid. And if you look at it and kind of in terms of second-order surface type effects, you can see it's all made up of cylinders and cones and ellipsoids, or slices of them. So you really can make interesting-looking objects out of this. Now we get to the nuts and bolts of how to draw one of these things. And we'll forge ahead, but I don't think I'll quite get done with this today, but I'll at least whet your appetite a little bit.
So in that last equation you wrote down on the left board, Q is supposed to represent the surface in what coordinate system?
This is the surface in screen coordinates, you might say. It's after the perspective and so forth. How are we going to draw one of these things? Drawing a surface requires 3 operations. Which pixels does it cover? So we know which ones we're going to color in. All these calculations have to be done in this perspective coordinate system. The screen coordinate system, right? Once we've figured out that a particular pixel is visible, lies inside the view, the outline of this thing, we want to know what the z depth of the object is at that point, so we can compare it to other things that might be visible there. That's likewise done in this perspective coordinates. And finally, once we've got all that, and we discovered that not only is the pixel inside the outlines of the thing, but it's in front of everything else after we've found this, we want to know what the normal vector is. So that we can calculate the lighting. This needs to be done in what you might call real coordinates or viewing coordinates or something. It's just the t without the p coordinate system. Now, in general, with these surfaces, you can take the sledgehammer approach. And that's quite often good to start out with, just to visualize what on earth we're doing here, and then try to refine it a little bit later. Which pixels does it cover and what is the z depth can sort of be solved simultaneously by taking actually, I'll even go so far as to put a 1 here for the W. Let's scan out all the pixels on the screen. Pixels at a particular pixel, XS and YS, standing for X screen and Y screen. We'll plug in X and Y into this thing. They're now constants for this particular pixel. We mush all this thing around, and this whole thing then collapses down into a quadratic equation in Z. Right? Basically, we're going to have to solve a quadratic equation for every pixel on the screen. If there are no solutions, or just complex solutions, then that means the thing isn't visible there. It's outside the boundaries of the circle. If there happens to be exactly one solution, that means we're just tangent to the surface at that point. And if there's 2 solutions, that means the line of sight pierces the thing. Yeah, 2 solutions. Here's the eyeball here like that. 2 solutions gives us something like that. 1 solution is where we are here, and 0 solutions is up there someplace. So for every pixel on the screen, we solve this quadratic equation. No solutions, throw it away, go on to the next pixel. 2 solutions, you take the nearest one. That's the z depth. And then you calculate the normal vector. Now, if you have lots of little spheres all over the screen and they're not too big, you're going to be wasting an awful lot of time by solving a quadratic equation every pixel, right? So let's see if we can smarten up this process a little bit to only deal with the interesting pixels. That is, somehow or other be able to figure out what the interesting range of pixels is right off, instead of wasting time on a lot of invisible ones. So let's find out what the silhouette outline of the picture is on the screen. What's the equation for the curve in just 2D xy coordinate space that this thing shows up within? Talk just about 3D surfaces, 4x4 symmetric matrices. What we're going to look for is a 3x3 matrix which represents the two-dimensional conic section, which is the outline of the sphere. Sometimes a little bit sloppy, and I say sphere here when I mean in general quadric surface, whatever it is that we're going to be looking at. So what we want is something of the form like this. This defines in xs and ys, x screen and y screen coordinate space, what the curve is. Q3 here means it's a 3x3 matrix. It's a 2D curve, 2D homogeneous curve. How do we come up with Q3? Well, we reach back a couple pages in our notes and we discover that someplace a little bit earlier on I was talking about the plane containing the silhouette outline of the surface. That's where the z component of the normal vector is 0, right? Is that Q. The original curve we want to draw times this column matrix. What this really is just we're extracting one of the columns out of Q. And that gives us the plane that this silhouette outline lies in. What we want to do is to intersect this circle, sphere shape, with this plane and project this thing onto the screen. We want to find out both where x, y, z, w times this thing equals 0 and x, y, z, w times q times x, y, z, w is equal to 0. Now, there's a simple way in which I'm going to just pull out of a hat here. Let's write down the equation this represents. ax plus by plus cz plus dw equals 0. What we want to get rid of is z. We're just projecting this thing on the screen. So let's solve this thing for z. Whoop, 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 whoop. Right? Z is now no longer a free variable if we're assuming that it lies in this plane. Given x and y, we can solve for z. So we will write the following magic expression. This is a tautology which I just constructed out of this equation. If you multiply it, you get x, y, minus a over cx, minus b over cy, minus d over cw, which is z, and then root w. This thing now we can plug into our original expression for the surface, and by tossing these two things in a bag and shaking it a little bit, we come up with the following thing. I need a little bit more room. Let me go over here. Got to be fast in this course. we have taken this 3 by 4 matrix times a 4 by 4 times a 4 by 3 matrix, and these things all multiply together properly, and you boil it down, you get a 3 by 3 matrix, which satisfies this equation, xyw times q3 equals 0. Q3 is now the equation for the 2D curve, which is this outline of this thing on the screen. In this case, x and y are the screen and the pixel coordinates. We left the w in there just to keep things homogeneous, but typically you'll plug in a value of 1 for the w. We now know the equation in screen space of the curve that we want to draw. So here's our screen, and here's the circle or whatever it is that Q3 represents. Now when we go through to scan this thing out, we are going to want to have basically two nested loops, one in y and one in x. The outer loop is going to go down one scan line at a time, and the inner loop is going to go across one pixel at a time, filling in the scan lines, right? So the next thing we would like to find out is, what is the range in y that we want to bother with here? We want to find the maximum y and the minimum y that this thing covers on the screen. How do we do that, given that we know what Q3 is here? Yes?
Do it again.
Effectively, you do this sort of thing again, but it's a slightly different order of things. The easiest way I've found to represent this, there are several ways of solving this thing of different amounts of complexity. Let's flip back in our pages again a little bit and notice the following thing. We start out with a circle, say, and a line. Lines represented by A, B, and C. How do we find out if this line is tangent to the circle? Tangent to the circle if the product of the line equation with the inverse or the adjoint, whatever you like, of this thing is equal to 0, right? That's kind of what we want here. We want to find out the two lines that are tangent to this thing that happen to be real horizontal. That is to say, these two lines, the equation of which are 0, 1, and minus y max, and 0, 1, and minus y min. These are the two tangent lines to the circle. We want to find out what values of y max and y min cause this horizontal line to be tangent to the circle. So we take the inverse of Q3, or the adjoint, if you will, and we multiply it by those two line equations, and come up with, abracadabra, a quadratic equation in y. Two solutions, one's the max and one's the min. Now, in fact, because we got this nice 0 here and a nice 1 here, you don't have to go so far as to take the entire adjoint of this thing just so you can multiply it by 0 later on. If you go into the to this thing and say, yeah, B, C. Let's look in with our little microscope at the innards of Q3 here. It's a symmetric 3 by 3 matrix. We'll give all the elements names here. I don't like to use lots of subscripts on names if I can avoid it, so sometimes I just go through and start naming things by letters of the alphabet. You multiply this thing by blah, 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 and you'll get D minus 2EY plus FY squared. Right? So really the only elements of this adjoint or inverse that we're interested in are D, E, and F. And if we, again, rename the elements of Q to start out with, this is Q star here. let me go into the innards of Q. And I'll call the elements of that by small letters. In order to come up with Q star, you do the get rid of the row and column and take the determinant of the remaining thing and flip the signs and garbage around like that. And you wind up discovering that. I did this before, so I don't have to think right now. That. These are the capital letters that are going to be the coefficients of the quadratic equation for y max and y min in terms of certain of the interesting elements out of the matrix Q3. We now know how to get the maximum and minimum y, so we've got the outer loop, and you'll have to stay tuned until next time to find out how to do the inner loop.
So you don't really need Q3 except that part of it?
It happens that the other elements of Q3 turn out to be interesting when you're computing normal vectors, or the z depth, basically. Next time, in fact, Ed Catmull will be here talking about a slightly different topic, and so you'll actually have to wait until next Monday to find out the remainder of this.
Is there ever a chance that we'll get those tutorials that you were going to get?
Tutorials.